Time itself is not the steady, universal rhythm we once believed it to be. A clock ticking on Earth does not match a clock near a supermassive galaxy. Scientists have now confirmed something profound. Time moves differently depending on where you are in the universe, not by milliseconds or fractions of a second, but by measurable, observable amounts that reshape how we understand cosmic history itself. Near massive galaxies, time slows. Events unfold at a different pace. What appears to us as billions of years might be experienced very differently elsewhere. This is not theory anymore. It is observation. If you want to understand how the universe actually works at its deepest level, subscribe and hit that like button. Let's explore this discovery together. For most of human history, time was treated as absolute. A second was a second everywhere, for everyone. Clocks might be imperfect, but time itself was considered a fixed backdrop against which events unfolded. Newton's universe operated this way. Time flowed uniformly, indifferent to location, motion, or the presence of mass. This view made intuitive sense. Our daily experience confirms it. A minute feels the same whether you are standing still or walking. The rhythm of life does not seem to depend on where you are or how fast you are moving. This assumption shaped science for centuries. Then Einstein arrived and everything changed. His theories of relativity revealed that time is not absolute. It is flexible, relative, and intimately connected to space, motion, and gravity. Time can stretch, it can compress, it can slow down or speed up depending on circumstances. This was not philosophical speculation. It was mathematics grounded in experimental reality. Special relativity showed that time dilates with motion. A clock moving at high speed ticks more slowly than one at rest. This effect becomes dramatic near the speed of light. Astronauts orbiting Earth age slightly slower than people on the ground. The difference is tiny, measured in fractions of a second, but it is real and measurable. General relativity extended this insight to gravity. Mass and energy curve space-time. The stronger the gravitational field, the more time slows down. Near a massive object, clocks run slower compared to regions farther away. This is not a malfunction of the clock. It is a feature of reality. Time itself behaves differently in different gravitational environments. Both predictions have been tested exhaustively. Atomic clocks flown on airplanes, satellites in orbit, and precision instruments on Earth all confirm the same result. Time is not uniform. It varies with motion and gravity in exactly the ways Einstein predicted. Yet for decades, these effects were studied primarily in controlled laboratory settings or within our solar system. The time dilation near Earth is measurable but small. Even near the Sun, the effect is modest. To see truly dramatic distortions, you need extreme gravitational fields. Black holes produce the most severe warping. Near the event horizon of a black hole, time slows so dramatically that an outside observer would see objects appear frozen, taking infinite time to cross the boundary. This effect has been confirmed through observations of matter spiraling into black holes and through gravitational wave detections from black hole mergers. But black holes are extreme, singular objects. What about galaxies? Galaxies are vast collections of stars, gas, dust, and dark matter, bound together by gravity. They contain billions or even trillions of stars. Supermassive black holes sit at their centers. The combined gravitational influence of all this mass is enormous. If gravity distorts time, then galaxies should create measurable time dilation effects across cosmic scales. This raises a question that sounds simple but carries profound implications. If we observe distant galaxies, are we seeing them as they are, or are we seeing them through a lens of distorted time? For years, this question remained largely theoretical. The challenge was not the physics, which was well understood, but the observation. Measuring time dilation across intergalactic distances requires extraordinary precision. You need to identify specific events, measure your timing accurately, and compare that timing to what would be expected in the absence of gravitational effects. Until recently, the tools to do this reliably did not exist. That has changed. Advances in observational astronomy, particularly in detecting and analyzing distant supernovae and quasars, have made it possible to measure cosmic time dilation directly. Scientists recently analyzed light from quasars, extraordinarily bright objects powered by supermassive black holes actively consuming matter. Quasars flicker and vary in brightness over time. By studying these variations across many quasars at different distances, researchers could measure how time behaves in different regions of the universe. What they found confirmed the prediction. Time near massive galaxies runs measurably slower than in less dense regions of space. The effect is subtle when measured across individual galaxies, but becomes pronounced when looking at the universe on larger scales. This is not just an academic curiosity. It has real consequences for how we interpret cosmic history. When we look at distant galaxies, we are looking back in time because light takes time to reach us. A galaxy 10 billion light-years away shows us what it looked like 10 billion years ago. But if time itself was running differently in that region due to gravitational effects, then our interpretation of how long events took becomes more complex. Processes that appear to have taken a certain amount of time from our perspective may have unfolded differently in the local time frame of that galaxy. This discovery forces us to reconsider the timeline of cosmic evolution. The formation of stars, the growth of black holes, the merging of galaxies, all of these processes are affected by local time dilation. In regions of intense gravity, these events unfold more slowly from an external perspective. This means the universe's history is not uniform. Different regions experience time differently. The early universe, dominated by dense concentrations of matter collapsing into the first galaxies, would have exhibited significant time dilation effects that we must now account for when reconstructing cosmic history. To understand why this matters so deeply, we need to step back and examine what time dilation actually means at a fundamental level. Time dilation is not an illusion or a measurement error. It is a physical reality baked into the structure of space-time. When we say time slows down near a massive object, we mean that all physical processes in that region genuinely occur more slowly relative to distant observers. Clocks tick slower. Light waves oscillate at lower frequencies. Chemical reactions proceed at reduced rates. Even biological processes, if life existed in such extreme environments, would unfold more gradually. This happens because gravity is not a force in the traditional sense. According to general relativity, gravity is the curvature of space-time caused by mass and energy. Massive objects create deep wells in the fabric of space-time. Time flows differently at different depths in these wells. Near the bottom, close to the massive object, time flows more slowly. Farther away, where space-time is flatter, time flows faster. The mathematics describing this are precise and unambiguous. The greater the mass and the closer you are to it, the stronger the time dilation effect. For galaxies, this creates a complex gravitational landscape. A typical galaxy contains hundreds of billions of stars, vast clouds of gas and dust, and an enormous halo of dark matter extending far beyond the visible galaxy. At the center sits a supermassive black hole, millions or billions of times the mass of the Sun. All of this mass curves space-time in intricate ways. Time dilation is not uniform across the galaxy. It is strongest near the central black hole and gradually weakens toward the outer regions. Different parts of the same galaxy experience time at different rates. When we observe distant galaxies, we are looking through multiple layers of this complexity. Light from a galaxy travels across cosmic distances, passing through regions with varying gravitational fields. The expansion of the universe adds another layer of time dilation, a cosmological effect distinct from but related to gravitational time dilation. Disentangling these effects requires sophisticated analysis and careful modeling. The recent confirmation of gravitational time dilation near massive galaxies represents a triumph of observational precision and theoretical understanding. The method scientists used involves studying objects whose behavior is well understood and can serve as cosmic clocks. Quasars are ideal for this. They flicker due to processes in the accretion disk surrounding the central black hole. These variations occur on timescales ranging from days to years. By observing many quasars at different distances and comparing how their light curves, the patterns of brightness changes over time, evolve. Researchers can measure time dilation effects directly. Light from more distant quasars is redshifted, stretched to longer wavelengths by the expansion of the universe. This cosmological redshift is well understood and expected, but embedded within this signal is an additional effect. If the quasar resides in or near a massive galaxy cluster, the intense gravity of that cluster causes additional time dilation. Events that take 1 year in the quasar's local time frame appear to take longer when observed from Earth. The light is not just redshifted by cosmic expansion, but also by the gravitational well the quasar inhabits. By analyzing thousands of quasars, scientists detected this signal clearly. The data showed that time near massive concentrations of matter runs measurably slower, exactly as general relativity predicts. This confirmation has several profound implications. First, it validates general relativity on cosmic scales in a new way. While the theory has been tested extensively in the solar system and through gravitational wave observations, directly measuring time dilation across intergalactic distances adds another layer of confirmation. The universe behaves as Einstein's equations predict, even across billions of light years. Second, it provides a new tool for mapping the distribution of mass in the universe. Time dilation effects encode information about the gravitational field. By measuring how time behaves in different regions, scientists can infer the presence and distribution of mass, including dark matter that cannot be observed directly. Dark matter is particularly important here. It does not emit, absorb, or reflect light, making it invisible to telescopes. We know it exists because of its gravitational effects on visible matter. Galaxies rotate faster than they should based on visible mass alone. Galaxy clusters hold together more tightly than the gravity of their stars and gas can explain. Gravitational lensing, the bending of light by mass, reveals dark matter's presence through its influence on light from background objects. C. Time dilation offers another signature. Regions with significant dark matter concentrations will exhibit stronger time dilation effects. By mapping these effects across the sky, scientists can create detailed three-dimensional maps of dark matter distribution throughout the universe. This approach complements other methods and provides independent verification. It also raises intriguing questions about how dark matter influences cosmic evolution. If dark matter halos around galaxies create significant gravitational wells, then time inside those halos runs slower than in intergalactic voids. This means processes occurring within galaxies, such as star formation, occur at different effective rates depending on the local gravitational environment. Galaxies in dense clusters, surrounded by vast amounts of dark matter, experience stronger time dilation. Their evolution, from our external perspective, appears slower. This has implications for understanding galaxy formation and evolution. The first galaxies formed in the early universe when matter was more uniformly distributed. As structure grew and galaxies clustered together, gravitational fields intensified. Time dilation effects became more pronounced. This means the pace of cosmic evolution is not constant. It varies across space and time, depending on the local gravitational environment. Early galaxies in dense regions may have evolved differently than those in less dense areas, not just because of different amounts of available material, but because time itself flowed at different rates. Another consequence involves our interpretation of cosmic events. Supernovae, the explosive deaths of massive stars, are used as standard candles to measure cosmic distances. The brightness of a supernova at peak and how that brightness fades over time follow predictable patterns. By measuring how bright a distant supernova appears, astronomers can determine how far away it is. This technique, applied to Type 1a supernova, led to the discovery that the universe's expansion is accelerating, a finding that earned the Nobel Prize and introduced the concept of dark energy. But supernovae are also affected by time dilation. A supernova occurring in a distant galaxy unfolds in that galaxy's local time. When we observe it from Earth, we see it stretched in time due to both cosmological expansion and gravitational time dilation. The light curve, how brightness changes over time, appears stretched. Events that take days or weeks in the supernova's local frame appear to take longer from our perspective. This effect was already known and accounted for in cosmological measurements. What the new observations add is a more detailed understanding of the gravitational component, allowing more accurate corrections and interpretations. Time dilation near massive galaxies also affects our understanding of black hole growth. Supermassive black holes at galaxy centers grow by accreting matter and merging with other black holes. These processes take time. But whose time? From our perspective, observing from a distance, processes near a black hole appear slowed. Matter spiraling into the black hole seems to take longer to cross the event horizon. From the perspective of the infalling matter, things happen normally. This mismatch creates observational challenges. When we see a supermassive black hole with 1 billion solar masses in a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago in our time frame. But in the galaxy's local time, affected by its own gravitational field, the actual elapsed time may differ. This becomes important when constructing models of how black holes grow over cosmic history. If we do not account for time dilation, we may misinterpret how quickly black holes accumulated mass. The same issue applies to star formation. Stars form from collapsing clouds of gas. The process takes time. In regions with strong gravitational fields, this process from an external viewpoint appears slower. This does not change the physics of star formation in the local frame, but it affects how we interpret observations of distant star-forming regions. The universe, it turns out, does not have a single clock. It has countless clocks, each running at slightly different rates depending on local conditions. Earth's clock, sitting in the relatively weak gravitational field of our Sun and the Milky Way, runs at one rate. A clock near the center of a massive galaxy cluster, deep in a gravitational well, runs at a different rate. The difference accumulates over cosmic timescales. Billions of years in one location may correspond to a different duration in another. This does not violate causality or create paradoxes. It simply means that time, like space, is not uniform. This realization connects to broader questions about the nature of reality. We experience time as a flowing river, carrying us from past to future. This subjective experience feels universal, but physics reveals a more complex picture. Time is a dimension, interwoven with space into a four-dimensional fabric called space-time. Events are not located in space at a particular time. They are located in space-time at specific coordinates that blend space and time together. Motion through space and the presence of mass distort this fabric, altering how time flows in different regions. The implications extend to the fundamental question of simultaneity. In a universe where time flows at different rates in different places, what does it mean for two events to happen at the same time? In special relativity, simultaneity is relative to the observer's motion. In general relativity, it is also relative to gravitational fields. Two events occurring simultaneously from one observer's perspective may not be simultaneous from another's perspective in a different gravitational environment. This is not a matter of perception or measurement error, it is a feature of how space-time is structured. For practical purposes on Earth, these effects are negligible. GPS satellites must account for time dilation because they orbit high above Earth where gravity is weaker and time runs slightly faster. Without corrections, navigation errors would accumulate rapidly. But in daily life, the difference between time at sea level and time on a mountaintop is imperceptible. The same cannot be said on cosmic scales. The time dilation between regions of different gravitational potential becomes significant. It affects cosmic evolution, observational astronomy, and our understanding of the universe's history. One of the most striking aspects of this discovery is that it was predicted more than a century ago. Einstein published general relativity in 1915. The equations clearly predicted gravitational time dilation, but confirming it across cosmic distances required technology and observational techniques that would not exist for another 100 years. This is a recurring theme in physics. Theory often runs ahead of observation. Mathematics reveals possibilities that experiments must later confirm or refute. General relativity has survived every test. Each new confirmation, from the bending of starlight during solar eclipses to the detection of gravitational waves to the measurement of time dilation near distant galaxies, strengthens our confidence that the theory correctly describes reality. Yet, mysteries remain. General relativity does not explain everything. It breaks down at quantum scales, inside black holes, and at the moment of the Big Bang. Physicists seek a more complete theory that unifies general relativity with quantum mechanics. Such a theory would describe how space-time behaves at the smallest scales and the highest energies. Time dilation, as described by general relativity, is a classical effect. It emerges from the smooth curvature of space-time. At quantum scales, space-time may not be smooth. It may fluctuate, foam, or have discrete structure. How time behaves in such a regime is unknown. The discovery of time dilation near massive galaxies also raises questions about cosmic evolution. The universe began in a hot, dense state and has been expanding and cooling ever since. In the early universe, matter was more evenly distributed. As gravity pulled matter together, galaxies and galaxy clusters formed. This process created regions of varying gravitational potential. Time dilation effects grew stronger in denser regions. This means the universe's history is not just a story of expansion and cooling. It is also a story of diverging timelines. Different regions of the universe have experienced different amounts of elapsed time since the Big Bang. This divergence is subtle when averaged over large scales. Cosmological models typically assume that time flows uniformly on average, which is a good approximation for understanding the overall expansion and evolution of the universe. But local variations exist. A galaxy cluster with a deep gravitational well has experienced less elapsed time than a void with minimal mass. The difference is not dramatic enough to cause major discrepancies in current cosmological models, but it is real and measurable. As observational precision improves, accounting for these variations may become necessary for accurate modeling. The concept of cosmic time itself requires careful definition. Cosmologists often refer to cosmic time, a time coordinate defined relative to the average expansion of the universe. It provides a useful framework for describing the universe's overall evolution. But cosmic time is an idealization. It assumes time flows uniformly for observers at rest with respect to the cosmic microwave background, the faint glow of radiation left over from the Big Bang. In reality, local gravitational fields perturb this uniform flow. Time dilation near massive galaxies represents one such perturbation. Observers in different gravitational environments measure different elapsed times since the Big Bang. An observer in a massive galaxy cluster, deep in a gravitational well, would measure a slightly shorter elapsed time since the Big Bang than an observer in a cosmic void, where gravity is weak. Both measurements are correct in their local frames. There is no absolute, universal clock ticking away the age of the universe. Instead, age is reference frame dependent, varying with gravitational potential. This is a subtle but important distinction that refines our understanding of cosmic history. Another fascinating aspect involves the interplay between time dilation and cosmic expansion. The universe's expansion stretches space itself, increasing distances between galaxies. This expansion also causes cosmological redshift, shifting light from distant objects to longer wavelengths. Cosmological redshift is often described as a Doppler shift due to galaxies moving away from us, but more accurately, it results from light traveling through expanding space. As space expands, wavelengths stretch along with it. This redshift includes a time dilation component. Processes in distant galaxies appear slowed when observed from Earth, not because of local gravitational fields, but because of the expansion of space itself. Gravitational time dilation adds to this cosmological effect. A quasar in a massive galaxy cluster experiences both cosmological time dilation from the universe's expansion and gravitational time dilation from the cluster's mass. Disentangling these contributions requires precise measurements and detailed modeling. The recent observations succeeded in isolating the gravitational component, confirming its presence and magnitude. This achievement demonstrates the power of modern observational techniques and the robustness of theoretical predictions. The tools enabling these measurements have advanced dramatically. Telescopes have grown larger and more sensitive. Detectors have improved in efficiency and precision. Data analysis techniques leverage computational power unimaginable a few decades ago. Surveys now observe thousands or millions of astronomical objects, providing statistical samples large enough to detect subtle effects. Machine learning and artificial intelligence help identify patterns and anomalies in vast data sets. These advances have transformed astronomy from a field limited to studying individual objects in detail to one that can analyze populations and probe cosmic-scale phenomena. Gravitational time dilation is not the only time-related effect astronomers must consider. Light travel time introduces another layer of complexity. When we observe a distant galaxy, we see it as it was when the light left, not as it is now. The farther the galaxy, the further back in time we see. This look-back time is a fundamental feature of astronomy. It allows us to study the universe's history by observing objects at different distances. But it also means we never see the universe as it is now. We see a patchwork of images from different epochs, stitched together by the finite speed of light. Combining look-back time with time dilation creates a rich but complex observational landscape. A galaxy 10 billion light-years away shows us what it looked like 10 billion years ago in our time frame. But the galaxy's local time, affected by its gravitational field, may have experienced a different duration. Processes unfolding in that galaxy appear slowed from our perspective due to both cosmological expansion and local gravity. Interpreting what we see requires accounting for all these effects. The recent confirmation of gravitational time dilation near massive galaxies provides the empirical foundation to make these corrections accurately. This discovery also has philosophical implications. Time, one of the most familiar aspects of human experience, is far stranger than intuition suggests. We perceive time as flowing steadily, carrying us inexorably from past to future. This perception is deeply ingrained, yet physics reveals that time is flexible, variable, and intimately connected to space and gravity. There is no universal now, no single moment that exists simultaneously everywhere. Instead, time is local, shaped by motion and mass. Different observers in different locations experience time differently. All perspectives are equally valid. None is privileged. This relativity of time challenges our intuitive picture of the universe as a three-dimensional space evolving through an absolute time. Instead, the universe is a four-dimensional space-time continuum. Events are not separate in space and time, but united in space-time. The distinction between past, present, and future, while meaningful to us, is not fundamental to the universe's structure. This view, sometimes called the block universe, suggests that all moments exist equally. The flow of time is a feature of our perception, not an objective property of reality. General relativity supports this interpretation, though it does not require it. Whether time truly flows or whether our perception of flow is an illusion remains a deep question. Physics describes how time behaves but does not fully explain why we experience it as flowing. Entropy, the tendency for disorder to increase, provides one possible explanation. The second law of thermodynamics states that entropy increases over time in closed systems. This gives time a direction, an arrow pointing from past to future. Our memories record the past, not the future, because increasing entropy creates irreversible processes that encode information about earlier states. But why entropy increases in the first place, why the universe began in a low entropy state, remains an open question tied to the Big Bang's initial conditions. The discovery of time dilation near massive galaxies adds another piece to this puzzle. It confirms that time is not an independent backdrop but an integral part of the physical universe, shaped by matter and energy. This reinforces the lesson of relativity. Space and time are not fixed stages on which events occur. They are dynamic, participatory elements of reality that interact with everything else. Mass curves space-time, affecting how clocks tick and how rulers measure. Motion and gravity distort time and space in predictable, measurable ways. The universe is a unified whole, not a collection of separate objects existing independently. Looking forward, this discovery opens new avenues for research. Improved measurements of time dilation across different cosmic environments will refine our maps of the universe's mass distribution. Combining time dilation data with gravitational lensing, galaxy surveys, and cosmic microwave background observations will provide a multifaceted view of how matter is distributed and how it has evolved. This is particularly important for understanding dark matter and dark energy, the mysterious components that dominate the universe's mass and energy budget. Dark energy, responsible for the universe's accelerating expansion, remains poorly understood. It behaves like a negative pressure, pushing space apart. Its nature is unknown. It could be a cosmological constant, a property of space itself, or a dynamic field that changes over time. Distinguishing between these possibilities requires precise measurements of the universe's expansion history. Time dilation measurements contribute to this effort by providing independent constraints on cosmic distances and the distribution of matter. Every new piece of data helps narrow the range of possible explanations. Time dilation also affects our search for gravitational waves. These ripples in space-time, produced by accelerating massive objects, carry information about cataclysmic events like black hole mergers. Gravitational wave detectors on Earth have observed dozens of such events. Future space-based detectors will extend observations to lower frequencies, detecting waves from supermassive black hole mergers. When these waves pass through regions with strong gravitational fields, they experience time dilation. The signal's frequency and duration are affected. Accounting for these effects is crucial for accurately interpreting gravitational wave observations and extracting information about the sources. The study of exoplanets, planets orbiting other stars, may also be touched by time dilation considerations. While the effect is tiny for individual stars, understanding the gravitational environment of distant planetary systems could become relevant as measurements grow more precise. If we ever detect signs of life on an exoplanet, understanding its local time frame and how it compares to ours adds an intriguing layer to interpreting observations. Life evolves over time. The pace of evolution depends on local conditions, including how time flows. This is speculative, but it illustrates how deeply time dilation is woven into the fabric of cosmic phenomena. Another frontier involves testing general relativity in ever more extreme conditions. While the theory has passed every test so far, physicists remain curious about potential limits. Does general relativity hold in the intense gravitational fields near black holes? Does it accurately describe the universe at its largest scales? The detection of time dilation near massive galaxies strengthens confidence that the theory works across cosmic distances. But as observations reach further and probe stronger fields, unexpected deviations could reveal new physics. Science progresses by pushing theories to their limits, seeking the boundaries where they break down, and new understanding must emerge. Time dilation near massive galaxies also connects to the study of cosmic voids, vast regions of space with very little matter. Voids occupy most of the universe's volume. They are not completely empty, but contain far fewer galaxies than average. The gravitational potential in voids is shallower than in dense regions. Time in voids runs faster than in galaxy clusters. This creates a cosmic landscape of varying time flow. Understanding this landscape helps map the universe's large-scale structure and provides insights into how matter has clustered under gravity's influence. The initial conditions of the universe, set shortly after the Big Bang, determined where matter would concentrate and where voids would form. Tiny quantum fluctuations, stretched to cosmic scales by inflation, seeded the structure we see today. Gravity amplified these seeds, pulling matter together into galaxies and clusters while leaving voids behind. Time dilation is a direct consequence of this gravitational clustering. Regions that collapsed under gravity created deep potential wells where time slows. Regions that remained sparse stayed relatively flat with faster flowing time. The universe's structure is not just spatial, it is also temporal. A tapestry of varying time flows reflecting the distribution of mass and energy. This temporal structure has practical implications for mapping the universe. Astronomers create three-dimensional maps of galaxy positions, tracing the cosmic web of filaments, clusters, and voids. Adding time dilation information adds a fourth dimension to these maps, revealing the gravitational landscape. This enriched picture helps test cosmological models and understand how the universe evolved from its early smooth state to the complex structure we observe today. Every additional constraint tightens the comparison between theory and observation, guiding refinements and potentially revealing surprises. The discovery also invites reflection on humanity's place in the cosmos. We inhabit a small planet orbiting an ordinary star in an average galaxy. Our local experience of time is shaped by Earth's gravity, the Sun's mass, and the Milky Way's gravitational field. This is our reference frame, the clock by which we measure cosmic history. But it is not the universe's clock. There is no single cosmic clock. Every location has its own pace, shaped by local gravity. Our measurements are valid within our frame, but they are not absolute. Other observers in other locations would measure different elapsed times, different ages for the universe, different durations for cosmic events. This relativity of time is humbling. It reminds us that our perspective, while valid, is not unique or privileged. The universe does not care about our clocks or our reference frames. It simply exists, following the laws of physics that govern spacetime's behavior. Understanding these laws requires stepping outside our immediate experience and embracing the counterintuitive truths that mathematics and observation reveal. Time dilation, once a theoretical curiosity, is now an observed feature of the cosmos, as real as the galaxies themselves. As technology advances, measurements will become even more precise. Next-generation telescopes, both on the ground and in space, will observe fainter and more distant objects. Improved detectors will capture subtle variations in light curves and spectra. Larger datasets will enable statistical analyses of unprecedented power. These advances will refine measurements of time dilation, mapping its variations across the sky with ever greater detail. We may discover unexpected patterns or anomalies that challenge current understanding and point toward new physics. The interplay between observation and theory is central to scientific progress. Observations test predictions, confirm or refute hypotheses, and sometimes reveal phenomena that no one anticipated. Theories organize observations into coherent frameworks, making predictions that guide future experiments. The confirmation of time dilation near massive galaxies represents this process in action. Theory predicted it. Observations confirmed it. The result strengthens our understanding and opens new questions to explore. One such question involves the detailed shape of gravitational fields around galaxies. While the overall effect of time dilation is now confirmed, the fine structure remains to be mapped. Do different types of galaxies, spiral versus elliptical, create different time dilation profiles? How does the distribution of dark matter within a galaxy affect local time flow? Can we use time dilation measurements to probe the inner structure of dark matter halos? These are frontier questions that current and future observations may answer. Another area of interest is the role of supermassive black holes at galaxy centers. These black holes dominate the gravitational field in the innermost regions. Time dilation near them is extreme, far stronger than the average across the galaxy. Processes occurring near these black holes, such as the accretion of matter and the launching of jets, unfold in a highly distorted time frame. Observing these processes from Earth involves interpreting signals that have been stretched by intense time dilation. Disentangling the intrinsic behavior from the observational effects requires careful modeling, informed by the growing body of time dilation measurements. The broader context of cosmic structure also matters. Galaxies are not isolated. They cluster into groups and larger clusters connected by filaments of matter stretching across millions of light years. These structures create a complex gravitational landscape. Time dilation varies not just from galaxy to galaxy, but across the entire cosmic web. Mapping this variation provides a dynamic picture of the universe's gravitational architecture. It reveals where mass concentrates, where voids exist, and how structure has evolved over billions of years. This dynamic picture connects to the universe's ultimate fate. Current observations suggest the universe will expand forever, driven by dark energy. As expansion accelerates, galaxies move farther apart. Eventually, distant galaxies will recede so fast that their light can no longer reach us. The observable universe will shrink. Regions of different time dilation will become increasingly isolated. Each galaxy cluster, deep in its gravitational well, will evolve at its own pace, cut off from the rest. Time dilation effects, while measurable now, will lose significance as cosmic isolation grows. The universe's temporal diversity will fragment into disconnected islands, each experiencing its own timeline. But that fate lies trillions of years in the future. For now, the universe remains connected. Light from distant galaxies still reaches us, carrying information about their history and their gravitational environment. We can measure time dilation, map its variations, and use it to understand cosmic evolution. This capability represents a triumph of human curiosity and ingenuity. From Einstein's theoretical insights to modern observational techniques, we have learned to read the universe's temporal landscape. Time is no longer a mystery but a measurable, mappable feature of reality. The philosophical implications continue to resonate. Time, so central to human experience, is not what it seems. It is not a river flowing uniformly everywhere. It is a landscape, varying with gravity, sculpted by mass and energy. This realization challenges deep-seated intuitions, but also enriches our understanding. The universe is not a static stage. It is a dynamic, interconnected system where space, time, matter, and energy interact in profound ways. Every discovery deepens this understanding, revealing layers of complexity and beauty. The confirmation of time dilation near massive galaxies is one such discovery. It validates a century-old prediction, demonstrates the power of modern astronomy, and opens new research directions. It reminds us that the universe is stranger and more intricate than everyday experience suggests, but it also shows that human reason, guided by mathematics and tested by observation, can uncover these hidden truths. Science is a process of asking questions, testing answers, and refining understanding. Each answer reveals new questions. Each discovery points toward deeper mysteries. Time dilation is no longer an abstract concept confined to textbooks. It is an observed phenomenon shaping cosmic evolution and our interpretation of astronomical observations. It affects how we measure distances, ages, and the history of the universe. It provides a new tool for mapping the cosmos and testing fundamental physics, and it challenges us to think beyond our immediate experience, to embrace a universe where time itself is flexible and variable. As we continue exploring the cosmos, time dilation will remain a central consideration. Whether studying galaxy formation, black hole growth, the distribution of dark matter, or the ultimate fate of the universe, we must account for how time flows in different gravitational environments. This is not a complication, but an opportunity. It reveals aspects of reality that would otherwise remain hidden. It connects local physics to cosmic scales, showing how the same fundamental laws govern everything from falling apples to the evolution of galaxies. The discovery that time moves slower near massive galaxies is profound. It confirms that time is woven into the fabric of the universe, shaped by gravity and variable across cosmic distances. It challenges our intuitions, validates our theories, and opens new frontiers for exploration. The universe has many secrets left to reveal. Time dilation is one we have now begun to measure and understand. And in understanding it, we glimpse the deeper unity of space, time, and matter that defines the cosmos. The story of how scientists confirmed time dilation near massive galaxies is also a story of technological progress and human persistence. The journey began with Einstein's equations, published when photography was still a novelty and computers did not exist. The mathematics predicted effects that seemed impossible to measure. Time differences across cosmic distances were real but tiny, buried beneath layers of other astronomical phenomena. For decades, these predictions remained theoretical, accepted because the underlying mathematics was sound, and terrestrial experiments confirmed time dilation in controlled settings, but not directly observed on galactic scales. The breakthrough required multiple technological advances converging. First, telescopes grew more powerful. Larger mirrors and more sensitive detectors allowed astronomers to observe fainter, more distant objects. Space-based telescopes like Hubble escaped Earth's atmospheric distortions, capturing crisp images of galaxies billions of light-years away. Spectroscopy improved, enabling precise measurements of redshift and other spectral features. These tools provided the raw data necessary for detecting subtle effects. Second, computational power exploded. Analyzing thousands of quasars, modeling gravitational fields, and disentangling multiple overlapping effects requires processing vast amounts of data. Modern computers and sophisticated algorithms make this possible. Machine learning techniques help identify patterns and filter noise. Simulations test theoretical predictions against observations. The computational infrastructure supporting modern astronomy would have been science fiction when Einstein first predicted gravitational time dilation. Third, statistical methods matured. Individual measurements of time dilation in distant galaxies are noisy and uncertain. But by averaging over large samples, statistical signals emerge. Scientists observed thousands of quasars at varying distances, each contributing a small piece of information. Collectively, these pieces revealed the signature of time dilation clearly and unambiguously. This statistical approach is characteristic of modern astronomy, where population-level studies reveal truths that individual observations cannot. The confirmation also required careful control of systematic errors. Many effects can mimic or obscure time dilation. Dust along the line of sight dims and reddens light. Intrinsic variations in quasar brightness can confuse timing measurements. Instrumental effects introduce noise. Each potential source of error must be understood and accounted for. Scientists validated their methods using simulations and cross-checks, ensuring that the detected signal truly represents gravitational time dilation rather than artifacts or confounding factors. This meticulous attention to detail is essential for establishing credible results. Another critical element was collaboration. Modern astronomy is a global enterprise. Telescopes around the world and in space contribute observations. Researchers from many institutions share data, develop analysis techniques, and scrutinize each other's work. Peer review ensures that claims are rigorously tested before acceptance. The confirmation of time dilation near massive galaxies represents the collective effort of hundreds of scientists working over decades. No single person or institution could accomplish it alone. Science is cumulative, building on past discoveries and collaborative efforts. The implications for cosmology extend beyond confirming general relativity. Time dilation measurements provide a new method for studying the universe's large-scale structure and evolution. Traditional cosmology relies on measuring distances and redshifts to map how the universe has expanded over time. Adding time dilation data enriches this picture, revealing the gravitational landscape and how it has shaped cosmic history. This multifaceted approach strengthens cosmological models and reduces uncertainties. One particularly exciting application involves constraining dark energy. Dark energy drives the universe's accelerating expansion, but its properties remain mysterious. Is it constant, or does it evolve over time? Does it interact with matter, or is it purely a property of space-time? Different models make different predictions for how time dilation should vary with distance and mass distribution. Precise measurements can distinguish between these models. narrowing the possibilities and guiding theoretical development. Every new constraint brings us closer to understanding what dark energy is and what role it plays in the universe's fate. Time dilation also intersects with the study of cosmic inflation, a period of rapid expansion in the universe's first moments. Inflation stretched tiny quantum fluctuations to cosmic scales, seeding the structure we observe today. These fluctuations imprinted patterns in the cosmic microwave background and influenced how matter clustered. Gravitational time dilation reflects this clustering. Regions that became dense under gravity's pull exhibit stronger time dilation. Studying this pattern provides indirect information about the initial conditions set by inflation. It tests inflationary models and connects the universe's earliest moments to its present structure. Another frontier involves gravitational wave cosmology. Gravitational waves carry information about the universe's expansion history. As waves travel through space, their wavelengths stretch due to cosmic expansion. This stretching, analogous to cosmological redshift of light, encodes information about the universe's evolution. Additionally, waves passing through regions with strong gravitational fields experience time dilation. Combining gravitational wave observations with time dilation, measurements from electromagnetic sources provides complementary perspectives on cosmic structure and evolution. This multi-messenger approach is revolutionizing astronomy, revealing phenomena that no single type of observation can fully capture. The discovery also highlights the importance of serendipity in science. While scientists set out to measure time dilation near massive galaxies, the techniques developed along the way often yield unexpected insights. Analyzing quasar light curves reveals not just time dilation, but also information about accretion disk physics, black hole masses, and the environment surrounding active galactic nuclei. Mapping gravitational fields using time dilation helps identify previously unknown galaxy clusters and refines models of dark matter distribution. Science rarely proceeds in straight lines. Pursuing one question often illuminates many others. Looking toward the future, upcoming telescopes and surveys promise even more precise measurements. The Vera Rubin Observatory will survey the entire visible sky repeatedly, cataloging billions of astronomical objects. Its data will enable time dilation studies on unprecedented scales. The James Webb Space Telescope observes the universe in infrared light, peering through dust and accessing wavelengths that reveal different aspects of cosmic structure. Space-based gravitational wave detectors like LISA will complement ground-based observatories, expanding the range of detectable signals. These instruments will push time dilation measurements to new levels of precision and scope. As measurements improve, subtle effects currently below detection thresholds may become observable. For instance, the internal structure of dark matter halos could create localized variations in time dilation that refined measurements could detect. The influence of cosmic voids, where time runs faster, might become measurable, providing insights into the universe's underdense regions. Even the effects of individual massive galaxies could be mapped in detail, revealing how time flows across their structures. Each refinement brings deeper understanding. The intersection of time dilation with other areas of physics also offers rich possibilities. Quantum mechanics and general relativity, the two pillars of modern physics, remain incompatible in extreme regimes. Time dilation is a classical effect, emerging from general relativity's smooth space-time. But at quantum scales, space-time may have structure that general relativity does not describe. Probing time dilation in extreme environments could reveal hints of quantum gravity, the sought-after theory that unifies relativity and quantum mechanics. The confirmation that time moves slower near massive galaxies stands as a profound milestone in our cosmic journey. It validates Einstein's century-old predictions across vast distances, demonstrates the precision of modern astronomy, and reveals time as a flexible dimension shaped by gravity throughout the universe. Each discovery deepens our understanding of reality's fundamental nature,